Friday. Those are the notes that we made on Friday. A space curve is a curve that exists in a three-dimensional space. Could you please keep quiet while I'm talking? So you're already familiar with lines, okay, because you did lines in vector geometry in first year. And those are space curves. But you get all sorts of space curves. Lines are just one. You get, some of them have specific names, like a helix or a, what was the other one I mentioned on Friday? A twisted cubic. But basically, any sort of wiggly line through space is a space curve. In a sense, curves that exist only on the xy plane are special cases of space curves, but they're such a special case that we tend not to use the term space curves for those. If you're saying space curve, then you're generally meaning a curve that really does exist in three-dimensional space and cannot be just drawn flat on the xy plane. Okay, so the way the sort of formulas work is you have something like that r of t with a little arrow on top of the r to show that it's a vector. Some people like to underline vectors. If you are good at doing boldface with your handwriting, you can do boldface, but in some way you need to indicate that that's a vector. A single real number gets put in, and what comes out is a vector. Okay, so you put in a real number, you get out a vector. You put in a set of real numbers, you get out a set of vectors. So what you're putting in is the parameter, and what you're getting out, you can think of as a point in space. So that r of t you can think of as an arrow that changes its direction and changes its magnitude as t changes, and your curve itself is the path mapped out in space by the tip of that moving arrow. Okay, so that's your space curve. You've got an arrow represented by r. As t changes, the vector that r spits out is going to be different. And so if you think of it as an arrow, it's an arrow that's changing its direction and probably changing its magnitude. And so you've got this moving, stretching, shrinking arrow, and you've got this curve mapped out in space. So that's what space curves are. We call those functions f, g, and h. We call them the component functions, and they are very ordinary sort of functions. There'll be things like sine t or t squared or something like that. Okay, there's the stuff about the arrow. Okay, and then I pointed out that if you have something written in Cartesian equations, so space curves can never be described with a single Cartesian equation. More than one Cartesian equation kind of bundled together, yes. But a single Cartesian equation, no. So if you see any geometric shape in three-dimensional space described by a single Cartesian function, it is not a curve. It's a surface, even if your initial sort of gut response is that it's a curve. And I gave three fairly typical examples there, because a year ago you would have said that those three things were curves. But they're only curves insofar as you can think of, so that x squared plus y squared equals 1 is a cylinder. And as that cylinder passes through the xy plane, in other words, where z equals 0, you get a circle. So when you think of x squared plus y squared equals 1 as a circle, in a sense you're thinking of the intersection between x squared plus y squared equals 1, the cylinder, and z equals 0, the plane. Okay, so if you set z equal to 0 in all of those, you will get curves. But that's what I mean by curves can be described by clusters of Cartesian equations. Because you could say the circle, the unit circle that's centered on the origin on the xy plane, you could describe it as x squared plus y squared equals 1, comma, z equals 0. So it's kind of a cluster of Cartesian equations. Okay, all right. So I made a bit of a meal of that, but I just know how easy it is to look at an equation that only has two variables in it and think it's a curve. But in this course, because we're so fixated on 3D space, it's a surface. Okay. All right, so there's a line. Nice typical line. It's a funny little squiggle there. Okay, so I want to carry on with space curves. Okay, I'm going to hand out registers. Just let me pause while I pause the... All right. Now, having spoken quite a lot about 3D curves, I'm actually just going to take a moment to look at two-dimensional curves, at curves in the xy plane, just to get us back into practice of dealing with parametrically described curves. Because just in the xy plane, if you are insisting that we're living in two-dimensional space, that we're setting z equal to 0 just by default, just like you do back in first year, if you do that, then curves drawn in the xy plane can be described in Cartesian form and in parametric form, and you can translate between them. So I'm just going to do a little exercise doing that. And I'm going to do exercise 21, 21 in the handbook. And I was doing green, wasn't I? Was it this shade of green? Was it that shade of green? I think it was that one, right? Okay. Okay, question 21a. Please keep quiet. Find a Cartesian equation for the curve described parametrically by this. So we just to begin with, just as kind of warm up, we're only considering curves in the xy plane. Notice how the z coordinate isn't even written there. If you wanted to, you could kind of think of there being an invisible z equals 0. But the fact that the z coordinate isn't even written means we are constraining ourselves to two-dimensional space. Okay? So whenever you've got a parametric expression and you want to turn it into a Cartesian expression, what you're looking for is relationships between the coordinates, or the coordinate expressions, the component functions. It's not so much what those component functions are. What's important is the relationship between them. For instance, if the first one had been 2 cos t and the second one had also been 2 cos t, I would have said y equals x. The cos t is important. It would have an effect on our curve. But the main thing that's happening there would have been that y and x were the same. So it's the relationship that matters more than what the functions actually are. What the functions actually are is important, but it's almost of secondary importance. So let's look at the relationship. In this case, we have x equals 2 cos t, and we have y equals 3 sin t. Now, you probably did exercises like this in first year. I hope that this is not the first time you're seeing this sort of thing. So cos t is x over 2, and sin t is y over 3. Cos squared t plus sin squared t equals 1 always. It's an identity. An identity is an expression that is always true. Doesn't matter what t is, sin squared t plus cos squared t equals 1. So therefore x over 2 squared plus y over 3 squared equals 1. What sort of a curve is that? It's an ellipse. And if we wanted to be very strict and say, hey, I really actually want to consider us working in three-dimensional space, we could include the z equals 0. If I gave you, not like today, but say in 2 weeks' time, if I gave you that expression over there on the right, left, that's left, on the far left here, if I gave you that and I said, what is that? I actually don't want you to answer ellipse. I want you to answer elliptical cylinder. Okay, because in 3D space, this is not a curve, this is so without the z equals 0, let's put the blank here. Without z equals 0, in 3D space, this is an elliptical cylinder. So like a circular cylinder, but you've squashed it a bit. So it's an elliptical cylinder. Okay. But as I say, this is just kind of warm-up. We're pretending that we're still in single variable calculus for a moment. Or single variable mathematics. Find a parametric description for the curve. Okay, so this is going the other way now. Given the Cartesian, find the parametric. Okay, this is a good old-fashioned hyperbola like you used to do at school. Like that. So what I'm going to do here is I'm going to say y is 1 over x. So what I'm going to do is I'm going to say let x equal t, and then it follows that y is 1 over t. Ooh, I need to go back to part A. I left something out. But let me finish part B. In other words, r of t is equal to t 1 over t. And because I'm wanting to restrict myself to x greater than 0, it means I'm restricting myself to t greater than 0. Yes, question? Cartesian equation is one basically involving x and y, or x, y, and z, involving your rectangular coordinates. Yeah. And a parametric equation or vector equation, they're essentially the same thing, they're written in vector form. So you'll see them either written with brackets or written with the sort of IJK notation of vectors, and they'll involve a parameter that's being plugged in, like t in the, well, I'm using t here, but I know when I teach first year maths I tend to use lambda for my straight line, so lambda is also a common parameter. Okay, the thing I left out here, and the reason why it occurred to me, is as I was starting to write my vector equation down here, I thought, oh, I must remember the parameter, and then I thought, hold on, in part A I ignored my parameter, let me look back, and in part A, sure enough, my parameter is important. It says t only goes from 0 to pi. So actually it's only the top half of my ellipse. If I drew it, it would look like that. Plug in t equals 0 into that. So my r expression is right at the top of the screen. Okay, if I plug in t equals 0, I'll get an x coordinate of 2 and a y coordinate of 0. There you go, there's my beginning point. If I plug in pi over 2, which is in the middle of my parameter range, I'll get x equals 0, y equals 3. Okay, and then t equals pi is going to give me that. It's only gone around once, half rather. In order to go around a full revolution, t would have to go from 0 to 2 pi. So in fact, that Cartesian equation I gave of x over 2 squared plus y over 3 squared equals 1, that describes a full ellipse. I'm actually only wanting to describe half the ellipse, so I'm actually going to put a comma y greater or equal to 0 into that, to make sure that that I'm quite clearly describing only that half. Okay, so good lesson there. Never ignore your parameter. If you're given a parameter, you need to see what effect it has on your curve. If you're creating a curve equation, you need to design your parameter so that it does what you want in your curve. It describes the piece of curve that you're actually wanting described. Okay, you give it a go. Number 22 and number 23. You try 22 and 23. I'll just scroll up so that you can see what I've done in case it's pertinent. But 22 and 23. How far should I go? Oops, too far. Pause. There's something quite structurally different between A and B here. In A and B, both my component functions were in fact functions more complicated than just t. Whereas in the second one, I just willy-nilly let one of my variables equal to t, and then the other one just followed along. I could have made y equal to t, and then x would have been 1 over t, and that would have been fine. You can kind of always do this. You can kind of always, if you're given a Cartesian equation and you want to develop a parametric equation, just simply let one of your variables equal to t and then just see what happens to the other one. But that method is a little bit problematic with any curves that repeat on themselves. Any curve that comes around and meets itself again, so anything that's like a loop, a circle or an ellipse, those sort of curves are quite poorly described by that method. Let's say I'd been given that ellipse equation and I'd wanted to develop the parametric equation, and I'd said, okay, well, let x equal to t. Okay, so I've got a t over 2 squared plus y over, and then I put everything to one side and I make y the subject. If you can just imagine doing that, you're going to end up with y equals plus minus square root something or other. What do you do with that plus minus? Do you put it as a plus minus square root into your expression? But what does that mean? Does that mean for every value of t you're going to get 1x and 2 y's? That's not really how curves work, because a curve is kind of describing a path of a particle through space, and it can only be in one place at one time. So then what do? Do you actually describe it as put the plus square root into one lot of brackets and a minus square root into the other lot of brackets and put a union sign in between? You can do that, But sometimes you end up with some really funny sign problems, and you have to end up using absolute values, and it basically ends up in a mess. So the sort of key rule of thumb here is that if your curve is something that's a loop, it's some sort of loop, it comes back on itself. It might be wiggly while it goes, but it meets itself again. Go for cos and sine. Cos and sine describe loops very nicely because of that repetitive behavior of cos and sine. So if your curve is a loop, cos and sine are your go-to parametric component functions. If it's some other curve that's not a loop, then that technique of just making one of your variables t and letting the others just follow along, that's often quite a good process. Okay, so in question 22, the trick is to make x the subject, not y. The reason for that is that just the way the little fractional powers work out, if you make y the subject, you kind of entrenching yourself into positive y's, just the way the little powers work out. Whereas just so happens if you make x the subject, negative y's are fine, but you'll always get out positive x's, which is what we want. If you make y the subject, you end up with x having to be positive because there's a square root in there, but the y that it gives you necessarily always being positive, and the parametric expression makes it clear that negative y's are possible. In 23 you should end up with something full of coses and sines, okay? So I'll just write a little note here. It's all to do with coses and sines. And then I had a couple of people ask me about the parameter. When you have one of these loops, we usually, unless there's some sort of special case, our t usually goes from 0 to 2 pi. 0 to 2 pi usually gives you a full revolution, unless it's not cos t, unless it's cos of 2t or cos of half t or something. But if it's just cos t sine t, 0 to 2 pi gives you a full revolution. Question? The actual answer. Okay, sure. The solution. Cool. And it will go up on Vula in 3rd or 4th period. You can also say t element of r. If you think of your curve as being a path that a particle is traveling through, t element of r just means the particle's always been traveling and will always be traveling, or will just keep going round and round this curve infinitely many times. A single revolution is generally what we're after. Question? In the white shirt? Yeah? Please keep quiet so I can hear the question. Oh, it's fine. It's fine. Yeah, so the cos and the sine, it's kind of just habit that the cos goes with the x and the sine goes with the y, because there are other parts of trigonometry and geometry where it has to be that way. But in describing a curve parametrically, it doesn't actually matter which is cos t and which is sine t. It just means that your particle starts at a different point in space, but it still goes around the same curve. So that was a good question, yes?
Can you please put up the answer to 22?
You're impatient. What have I got here? I've got x equals y to the power 2 over 3. Notice how negative y's are fine, because what does that mean? That means we're going to take y, we're going to square it, and then we're going to cube root it. Negative numbers, you can square and cube root, it's fine. But of course you will get out something positive because you're squaring something and then you're taking the by definition positive cube root. Yes. You wouldn't need to have restrictions on that because t went on forever, so x and y are also going on forever. Question. If it was the other way, if you made y the subject, you end up with something that looks like this. Okay, please keep quiet. Now there you're saying x, we're going to take x, we're going to cube it, and then we're going to square it, which means, square rooted rather, which means x has to be positive because we're going to be square rooting it. So so that expression insists on positive x's, which is fine. Positive x's we're fine with. But we will get out a positive y because we're taking a positive number, we're cube rooting it, and then we are by definition taking the positive square root. That little half fraction refers to the positive square root. That's the definition. So that means you have to put in positive x's and you're going to get out positive y's, but we know from our parametric expressions that negative y's are possible. Yes?
It's not 3 over 2, but exactly the same thing with the x and y axes.
No, I think it is 3 over 2. I think you'll find it is 3 over 2. Are we missing one another? Possibly I'm not understanding what it is that you're saying, but we do have to move on. So we can talk later if we're not quite, if our minds aren't meeting in the middle. Okay, I have to move on. I have to move on. And that's the problem with such a huge class. You ask such fabulous questions, and I just want to spend the entire lecture period answering your questions, and I just can't. We just simply don't have the time, which is hugely frustrating, but we need to carry on. Okay, all right. Drawing space curves. Not everybody's favorite thing to do, okay? If you could please keep quiet. Drawing curves, drawing space curves. So actually, now we really are moving into 3D stuff after that little bit of practice with the 2D stuff. Okay. If you're given, please keep quiet. If you're given the vector function that describes a space curve and you want to draw it, a little bit of a trick of how to draw it is to consider the projections of your curve onto the 3 coordinate planes. Okay. A trick to drawing space curves is to picture the projections of the curve onto the 3 coordinate planes. Or, in other words, and they're quite other words, but they achieve the same result, basically carrying on from the 2, to picture the curve as the intersection of 3 surfaces orthogonal to the coordinate planes. And that might sound like 3 quite different things, and I suppose visually it kind of is, but it achieves the same result. Okay, I'm going to do an example with exercise 26. I probably won't do all of them because there's 4 there and that's quite a lot. I'm actually going to skip the first one because the first one is a straight line, and straight lines you really know an awful lot about, and you can draw those quite easily. Straight line. It's actually probably easier to actually plot a couple of points there and then just join the points with your ruler. Probably easier to plot 2 points and try and plot them as accurately as you can. So let me actually rather use my time. Something a bit more pertinent. What's B? Okay, B is a great one. There we go. What does B look like? R of t equals cos t, sine t, 3t. And by the time you're halfway through this course, I want you to look at that and know what it is. Okay, because that's an iconic curve. Okay, you're looking at it now and you're thinking, I'll never reach that point. That looks completely opaque to me. But actually it's not if you just break it down into bits. Let's look at the projections of that curve. Now that's a curve, okay? It's like a piece of wire. It's like a piece of string. It's like you've got a particle moving through space and it's leaving a trail behind it, and the curve is the trail, okay? It's not a surface. It's not something if you drew it that you'd be able to color in, okay? It is a curve. Alrighty then, let's look at its projections onto the 3 coordinate planes. The xy plane, the xz plane, and the yz plane. And the way you do that is by taking each of your, the kind of variable that's left out, you set it to 0. Well, is that what we want to do? Not exactly. What we want to do is we want to kind of ignore that variable and not set it to 0. Ignore it and look at the other two. So xy plane, let's look at the x coordinate and the y coordinate. The x coordinate is cos t, the y coordinate is sin t. If we're just looking at those two, what's the relationship between them? The relationship between cos t and sin t is that cos squared t plus sin squared t equals 1. So x squared plus y squared equals 1. Okay? That's a circle in the xy plane of radius 1. Okay, what about the xz plane? Xz plane, we ignore the y coordinate. We just look at x and z. X is cos t, y is 3t. So, let's have a look. So, t would be z over 3. So, x is cos of z over 3. It's a cos curve. It's a cos curve that has x as the dependent variable and z as the independent variable. So, it does this. Strictly speaking, of course, we wouldn't call that a function. And, of course, where it cuts on the vertical axis is going to be affected by that division by 3. But I'm not going for details here. I'm going for shape. YZ plane, very similar. Only this time y will be sine of z over 3. Here's y. Here's z. Sine curve. So it goes like so. So, you can think of our curve as floating in space. So coming back to our coordinate system in the classroom, here's the x-axis, here's the y-axis, here's the z-axis. If you look down the curve, you're seeing it projecting a circle onto your xy plane. If you look towards the xz plane, you're seeing wiggly, 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 wiggly. And if you look towards the YZ plane, you're seeing a slightly different but very similar wiggly wiggly. What is our curve? Okay, I won't call you on it, so you can lie if you want. Who thinks they know what kind of curve it is? Not many. And some hands are going like this. Is that a question? No, that you know what kind of curve it is. And it is in fact a helix. Okay, now you can recognize a helix equation straight off the bat because of the 3 component functions. One is a cos, one is a sine, and one is linear. Okay, and the linear one gives you the axis that your helix has as its axis of symmetry, or at least the axis that the axis of symmetry is parallel to. So the linear one gives you the direction that your helix is going, and then the other two contribute to the roundy nature of the helix. Okay, so cos, sine, linear, it's a helix. Doesn't really matter where the linear goes, in the x, the y, or the z position. Cos, sine, linear, it's a helix. Okay, but, so I did that all in terms of projections. Remember I had that in other words, and I said you could think of it as the intersection between 3 surfaces. You can think of this curve as being the intersection. Alternately, the curve is the intersection of a circular cylinder. Circular, sorry, I'm not writing very well here. So instead of thinking of the projection onto the xy plane as being a circle, you can think of the curve being lying on a circular cylinder. Intersection of a circular cylinder and 2 sinusoidal sheets. Yeah, and I'm not going to go into detail. If you were actually trying to describe that in detail, you'd say something like the one sheet is orthogonal to the xz plane and the other one's orthogonal to the yz plane, but I don't want to spend lots of time writing. If you look through old exam papers, you'll see it's a very common question. It'll give you a curve, it'll call it C, and then it will say, give 2, possibly 3 surfaces that the cylinder, that the curve lies on. It's a very, very typical test and exam question. And it's usually phrased in terms of intersecting surfaces, not in terms of projections onto coordinate planes. Yes, question?
When we get to quite funky shapes, will we be expected to draw them in 3D?
Yes. The question, if you didn't hear it, was when we get to quite funky shapes, will we be expected to draw them in 3D? And the answer is yes. We will expect you to draw some quite complicated curves in 3D. So brace yourselves. Okay, given that, according to my clock, there's 1 minute left, so let's just... No, I'm going to squeeze in 26C because it's very fast. Notice how 26C is very similar, they've just taken away the linear. Okay, so we're still going to have that circular projection onto the xy plane, but we're no longer going to have that sinusoidal look if you're looking from the side. Z is constant. So that means our curve, whatever our curve is floating in space at constant Z. You can think of your curve as being made up of infinitely many points, and every single point has a Z coordinate of 3. So it doesn't go up or down, it stays on Z equals 3. So if you drew it, it looks kind of like you're giving the Z axis a halo. Okay, I'm giving a little gap there just for artistic license. Of course, the curve does not actually have a gap. So that's just a circle. That curve is a circle, but it's a circle that exists at Z equals 3. So if you were wanting, for instance, to describe it in parametric form, in Cartesian form, you'd write that. Not just the x squared plus y squared equals 1, but the Z equals 3 as well. Okay, there we go.